So in the last video, we talked about the pH and the pH scale. We're going to start today, in this video, talking about the pOH. So as we discussed previously, the P in pH is just telling us to take the negative base 10 logarithm of the quantity. It's just a mathematical shorthand, essentially. It's a mathematical function. And so if we wanted to have other P scales, we're perfectly able to do that. And one common example of other P scales is the pOH. Now the pOH is exactly the same as the pH, only now we're considering hydroxide instead of considering hydronium. So the pOH is the negative log base 10 of the concentration of OH minus instead of H plus. You will also sometimes see the pKw, not quite as often because it's just a single value. It's not actually a scale since the kW is just one number. But that is another thing that you'll see crop up from time to time. So when we're looking at each of these things, there's some interesting stuff that happens when we're using all of these P values together. So we've discussed in the previous video how the concentrations of H plus and OH minus, when multiplied together, are equal to the equilibrium constant for the autoionization of water, and that constant is equal to 1 times 10 to the negative 14. If we just take the negative log base 10 of everything in that equation, this is what it would look like. So we would have the negative log base 10 of H plus the negative log base 10 of OH minus is equal to the negative log of kW, which is equal to 14. Because when you take the negative log base 10 of 1 times 10 to the negative 14, it is 14. And just kind of interestingly, if you remember your high school algebra, if you take the log of two things that are multiplied together, they end up being added together. It's just the way the math works. So they were multiplied together up here, but the log values are added together. This is actually the main reason why log scales were used so much a few decades ago, before computers became much more prominent, and you could have a computer in your calculator. The log scales were actually very handy for doing higher order multiplications. If you could use the log scale, it's easier to add it together. Anyway, so if we take this and we go ahead and simplify it, which is to say we insert P anywhere there is negative log base 10, we end up with the pH is equal to the pH plus the pOH is equal to 14. And that is actually really handy, having this the pH. I keep wanting to do that. pH plus the pOH is equal to 14. Because if we know one of those two, if we know the pH, then we automatically also know the pOH, and vice versa, since the two of them added together will always equal 14. So if we have something like this, where we say the pH is equal to 8, what would the pOH be? Well, I know that if the pH is 8, if I add that to the pOH, it will be equal to 14. And so if you do that simple bit of algebra there, the pOH is 6. 8 plus 6 gives us 14. So that is going to be very handy for us later, especially when we start talking about weak acids and bases and trying to compare values from pHs to pOHs. This is a lot easier than converting back into H plus and then converting H plus into the concentration of OH minus and then taking the negative log of that. That's a whole three-step process. This is much faster and easier. Alright, just very briefly here, I want to mention a few different things that you come across in your everyday life and what their pH values are, because we often think that, acidic things and basic things, that's just chemistry stuff. That's not stuff that we deal with all the time. When in reality, we deal with things that have relatively high and low pHs on a pretty regular basis. So for example, inside of you right now, there is stuff that is at a pH of around 2. 3 to 2. So you can see there's gastric juice and stomach acid. 3 to 2, round in there is the pH of stomach acid, which is pretty acidic. That is decently acidic, which it needs to be to break down some of the molecules that you eat. But even something like wine has a pH of around, and it does vary a little bit from one wine to another, but not greatly. Most of them are going to be somewhere around 3.5 or so. 3 to 4, something like that. Probably a little bit closer to 4 than to 3. But that's, again, decently acidic. Coffee, most people know, is acidic because your dentist bugs you about it if you drink coffee. I'm not a coffee drinker, and I still hear about how coffee is acidic. So those of you that are coffee drinkers, I'm sure you hear it all the time. But coffee is acidic, and it will eat away at your tooth enamel, which is why your dentist gets on to you about it. And most people don't realize, but actually even rainwater. Rainwater is considered to be this, this pure drinking water, straight from heaven. There's not any better stuff that you could drink. It's the most pure stuff out there. No, actually, it's not. It's actually not that pure at all. Rainwater usually has a pH of around 5.5. And this is mainly because as the water is up in the atmosphere, it absorbs CO2. And CO2, when it is absorbed into water, some of it, not all of it, but some of it will react with the water to form carbonic acid. And that acidifies. Excuse me. That acidifies the rain, giving it its acidic nature. And this is in the best of cases. If you live in a big city, which I wouldn't consider Tulsa to be too terribly big, but especially if you live in a really big city like Los Angeles or Hong Kong or other city like that, or Beijing, some city where there's a lot of driving, especially, where there's a lot of exhaust that's being put into the atmosphere. The smog that you get in those really big cities has a lot of nitrogen and sulfur compounds in it, and when those mix with water, they don't form carbonic acid, they form sulfuric acid and nitric acid. That's where you get really nasty acid rain. It's from that type of situation. In terms of bases, most people know that baking soda is at least a little bit basic. Most people might not realize that your blood is actually slightly basic. Just slightly, and it is very highly controlled. If your blood pH levels get out of whack, you are going to be in really big trouble. You could very easily die from your pH levels getting off by very much at all. Your body has a very complex buffering system in place in your blood to keep the pH at a very highly controlled level. And we'll talk more about buffers later in this chapter. But a few other things that you might not realize are bases. For some reason, most people that I talk to think that ammonia is an acid. It is not. It is actually a decently strong base, ammonia. Ammonia should, I would suggest, not be used as a cleaning fluid. Not because it doesn't work necessarily, mainly because ammonia can react with certain other cleaning fluids very badly, like as in kill you with deadly gases badly. So I would suggest using some other cleaning fluid other than ammonia most of the time. Bleach is kind of the same way. I do personally use bleach every once in a while to clean stuff, but only if it's something where I know something really nasty has been put on a surface, for example. And I have small children, so nasty things end up on surfaces. And so bleach is the last line of defense, not the first choice for cleaning things, because bleach is really nasty. Not necessarily because it's terribly basic, although it is actually quite basic, but it's also extremely reactive, and it can react very poorly with other stuff as well. So just be very careful with those cleaning fluids. People kind of get comfortable with them because, oh, I've been using bleach forever to clean this and that, and then you accidentally mix it with some other cleaning fluid and it produces mustard gas, and now you're gone and your family is devastated, and it's not good. It's very, very bad. So just be very careful with those. Okay, can get off my soapbox for a minute. So, how do we measure the pH? We've talked about the pH. We've talked about the significance and how the concentrations of these molecules vary from one pH value to another. Let's talk practically, how do we actually measure it? Well, there's a couple different ways we can do this. And the choice that we make as to how we're going to measure the pH mainly depends on how accurate we need to be. If we don't need to be very accurate, so if, for example, all we want to know is it acidic or is it basic, we don't care at all what the pH actually is, we just want to know which side of 7 the pH is on, then we can use litmus paper. And litmus paper, the most basic form of it anyway, or I shouldn't say basic, the simplest form of litmus paper comes in a red and blue variety, and if you put a red litmus paper into a basic solution, it turns blue. And if you take a blue litmus paper and put it in an acidic solution, it turns red. So this is very much just a yes-no answer. It does not tell you the relative pH or anything like that. All it tells you is it is acidic, it is basic. And if you want to know one way or the other, you have to have both. So if, for example, you have only red paper and you stick red paper into a solution and the color doesn't change, that doesn't necessarily mean that the solution is acidic. You would think, oh, it didn't turn blue, that means it's not basic, so it must be acidic. Not necessarily, it could just be neutral. So if it was just a neutral solution, it wouldn't change color then either. So they each only give you a yes answer. They each only tell you, yes, it is this. They can't say no. Other than, I guess, if they give you a yes, that is also giving you a no. But anyway. Another choice that you could use is an indicator. And indicators, like the ones shown here on the left side of the screen, are more accurate than litmus paper because they sometimes can give you an idea of the pH. Some of them are better than others at doing this, but they're not terribly accurate. So, for example, bromothymol blue, around a pH of 7, turns to green, and then when you get up to 9, it turns to blue. And so that does give you a general idea of the pH of the solution, but it's only a general idea. Same type of deal here with methyl red, going from yellow and then gradually becoming more and more red as you go to lower pHs. Phenolphthalein is the one that we most commonly use in the chemistry lab, and it does not start turning pink until around the pH of 8. And at that point it's very difficult to see still. But once it becomes basic, it becomes more and more pink. And the main reason we use phenolphthalein is, number one, it's cheaper than most of the other kind, and we can dispose of it easily. But most of the time we are actually just concerned with when does something become basic or when does something become acidic. And so the fact that it changes color right at 7, right around 7, is quite useful. The best way, though, to measure the pH is to use a pH meter. And these are conductivity probes. They measure the conductivity of a solution, but they are specially made to only measure the conductivity due to hydronium. So if you have something else mixed in, like potassium chloride or something like that, it will not measure the conductivity from those ions. it only measures the conductivity due to hydronium. I'm actually not sure how it does that, so if you ask me, I won't be able to give you an answer. But feel free to look that up if you're curious. But that is how a pH meter works. It actually measures the conductivity due to hydronium and just gives it to you on a screen. And that is by far the easiest and most accurate way to measure the pH. And so when possible, we use pH meters. All right, we're going to call it there for this video. In the next one, we're going to talk a little bit more about strong acids, which is a topic we mentioned earlier in the chapter, but we're going to dive into that a little bit more in the next video. So I'll see you there.